There's different pieces. So prior to 0, something's happening, and then after 0, something else is happening. I don't know if that's exactly what this one looks like, probably not. But because there's a jump from one function to another at 0, this is the questionable continuity. The way I drew this one, is it continuous? No, right? There's a jump there. There's a jump caused by the piecewise function jump. Versus I could draw a piecewise function that ends there, and the other one technically would start with an open circle and do that. Still, that's a point of interest. Is this one continuous? Yes, it is. Continuous means I don't have to pick my pencil up off the paper. So I can do this and this without picking my pencil up off the paper. Here, I can't. I have to pick it up, come down here, and begin again. So the critical thing that we have to look at is where does one function end and where does the other function begin? And if one ends at the same point that the other begins, it's continuous. If one ends at a different point, then it's not continuous. So this one ends at 0, comma what? So if I plug 0 into here, what do I get? -5. On this one, it starts at 0, comma -5. So since this one ends and starts at the same point, this, yes, would be continuous at 0. Okay? This one, we transition from one function to another. This one ends at 0, comma what? -4. This one begins at 0, comma -4. So that's another yes. Okay? This one ends at 1 what? 0. This one begins at 1, comma 0. But those are both open circles. So if I look at a graph, and I don't know exactly what this would look like, but this one's ending at 1, 0, and this one's beginning at 1, 0. And then here's an actual point at 1, comma what? 0. So right at 1, we fill that hole with the point 1, 0, which creates the continuity. So is this continuous at 1? Yes. Okay? Last one here. This one ends at 1 what? 1, 1, right? Because I'm plugging in 1. Is everyone good with that? This one starts with an open circle still at 1, 1. And this one fills it, 1, 1. Okay? But sometimes it'll be like 1, comma 3. So it would end at 1, 1, start at 1, 1, but then you'd have a random remove point at 1, 3. And that one would not be continuous. These just are all happening to be yes, but I don't think we're going to find that today on your notes. Okay? All right, so in your note packet, last page, determine for what numbers, if any. Now, I just focused on the points of transition. This is a little bit more in-depth than than the ones I just went over in the homework, because there's actually 2 points of transition. At 0, we jump from this function to this function. At 1, we then jump from this function to this function. So we've got 2 potential points of discontinuity to look at. So you're going to say that this one ends at 0, comma what? 0, comma 2. Good. This one begins at 0, comma 2. So the conclusion we have at 0 is that it's continuous at 0. And then another point of transition at 1. So this section ends at 1 what? 1, 2, because that's a constant. So if you plug in 1, you get 2. And this one begins at 1, 1, 3. If I plug in 1 here, I get 1 squared plus 2, which is 3. So because these, one ends at 1, 2, and the other one begins at 1, 3, there's a little jump between those points, and therefore this one is discontinuous at 1. Okay? What points would we check here? What do you think, Bean? Which points would we have to check? Well, we're checking 0 because this function ends at 0 and this one begins at 0. And then what other x value should we check for continuity? At what number do we jump from the second function to the third function? At 2. So 0 and 2 are what we're going to check. Okay? So this one starts at 0 what, Mike? Nope. If I plug in 0, what's 2 times 0? Starts at 0, 0. And this one ends at 0 what, Alyssa? Oh, I screwed up my starts and ends. I'm sorry, I screwed up my ends. This one is ending at 0. Well, because this, so let's back it up. Back in the day, you used to graph piecewise functions. So anytime x is less than or equal to 0, which is here and this direction, we're following a linear that's 2x. So up 2 over 1, up 2 over 1, up 2 over 1, y-intercept of 0 with a closed circle on the end. So this one's interval is ending at 0, 0. And I know it's 0, 0 because I am ending at an x-coordinate of 0. And I plug in that x-coordinate to see what the y-coordinate is. This is a parabola that's been shifted up 1. So in its entirety, it would look something like this. But we only want to see it between 0, which is here, open circle, and 2, which is here. So this particular section, when we're jumping from this one ending at 0 to this graph, which is starting at 0, this one is starting at 0, comma, and you just plug in your 0 to figure out where that endpoint is. 0 squared plus 1 is 1. So are the endpoints and the starting point the same? No. And so you can see visually, if you want to take the time to draw it out, you can see visually that there's a jump happening, but if the points don't match, you should know conceptually that there's going to be a jump there. So this would be discontinuous at x equals 0. Did that answer your question, Ryan? Because that's where one ends and the other begins. Now for the next one, it's ending at 2, beginning at 2. So I want to, for the second one, this one is ending at 2 comma what? 5. She's just plugging in 2 to get that, 2 squared plus 1. And this one is starting at 2 comma 5. 7 minus 2 is 5. So if it's ending and starting at the same point, so this one, and visually you can look up here, this parabola section, the x squared plus 1, ended at 2, 5. Well, this linear section is starting at 2, 5 with a slope of negative 1. So there's where it's ending and starting, hence why the continuity is there. So this is continuous at 2. Okie doke. Okay. Anybody still have questions? because we're dealing with all linears and quadratics, linears are always continuous. Quadratics are always continuous. Linears are always continuous. So within the interval, any place less than 0, we don't have to worry about. Any place between 0 and 2, we don't have to worry about because the quadratic doesn't have any jumps. And anything beyond 2, we don't have to worry about because lines are always continuous. So with piecewise, it's almost always going to be the points of transition that are worth looking at. When you jump from one image to the other, are you actually jumping, or is one ending exactly where the other one is beginning, maintaining that continuity? Okay? So if you look at 3, it wants to know for what value or values of A will this function still be continuous at 2? So they are essentially telling us to figure out what the A value is going to have to be in order for this to maintain its continuity at 2. And if you're maintaining continuity, then this one ending at 2 comma something has to be the same point as this one starting at 2 comma something. Which one of those can you figure out? The ends at or the starts at? Starts at, right? This one, because that is a complete function. This one's missing an A value that we're going to hunt for. But this one is clearly starting at 2 comma 5. So we essentially want that to equal 5. So when we plug a 2 in for our x up here, this one, 1 plus 2 squared. Okay? So this one, we want that to be a 5 if we're going to keep it continuous there. So when we plug in a 2 up here for x, we want that to still equal 5. So you would bring your 2 in here, and a plus 2, we want to equal the 5 that this one does. And so therefore a has to be, so a has to equal 3, and there's your answer. Because if a equals 3, then this one would end at 2 comma 5. Does that make sense? Okay, just making you think of it from a different angle. And then 4, similarly, is going to ask it from just a different vantage point to make sure we kind of can understand this from all directions. Find the value or values of a so that this function is continuous on the interval from negative infinity to infinity, which essentially means everywhere. So when would this function be continuous everywhere? What would a have to be? So essentially, when I plug in a here to get my y value, and I plug in a here to get my y value, I need those y values to be the same. Yes? So if I plug in a, and actually let me show you what visually is happening, not that you'd ever do this, but this one is a parabola. I'll show you on a calculator. X squared plus 2x. There's the parabola and here's the line. We're pretty much gonna have to answer at what a value would we have to stop this interval, the quadratic, would we have to stop the quadratic and start the linear in order for continuity to exist? I mean, I think it's pretty clear that it's -1, right? If this parabola was held on to up until -1, and then we jumped ship from the parabola to the line at -1, we would maintain continuity. So visually it makes sense, but algebraically, again, your input has to be a comma, and it would be a squared plus 2a, right? That's where that one ends. And this one starts at a comma -1. If we want to preserve continuity, we want those points to be matches. So we want those two y coordinates to have to be equal. So I plugged in a to the first one to get my y coordinate of a squared plus 2a. I plugged in a to the second one to just get -1. And then those two y coordinates need to equal each other. So a squared plus 2a needs to equal -1. If you solve that quadratic, you have to add your 1 over. You have to factor a plus 1 times a plus 1 gives you 0. And then tee it up, a equals -1, which is what we visually gathered from the graph. Any questions on that? That's it, right? Okay, so I'm going to pass out your homework. Oh, you definitely do all of it. Faith, I'm giving you Sarah's and Laura.